First, let's see just how clear the word random really is. Imagine a bag containing balls numbered 1 through 10, and suppose we draw one uniformly at random. 5 of the 10 outcomes are even, so the answer is 1/2. It is also clear exactly what we are counting equally. But once we enter a continuous world filled with infinitely many points and lines, even the word choose starts to wobble. In 1889, French mathematician Joseph Bertrand planted that very ambiguity in a probability textbook. Bertrand's box paradox was a story where intuition missed a single answer. Today's chord problem is even stranger. 3 different solutions produce 1/3, 1/2, and 1/4, and all 3 are logically valid. All we need is one circle, one inscribed equilateral triangle, and one criterion for deciding which chords are longer. Draw a chord at random in a circle. What is the probability that it is longer than a side of an equilateral triangle inscribed in the circle? The trap is not in the definition of a chord. It is hidden in the single word random. To compare 3 notions of randomness, we first need one length test that works for every chord. A diameter, which passes through the center, is the longest chord. The closer a chord moves toward the circumference, the shorter it gets. So a chord's length is determined completely by the distance from its midpoint to the center. In this diagram, orange marks the inscribed equilateral triangle, and the teal dashed circle is the boundary with radius 1/2 of r. Let r be the radius of the outer circle, and let d be the distance from the center to the chord's midpoint. Connecting the center, one endpoint of the chord, and the midpoint forms a right triangle. The Pythagorean theorem gives us the length immediately. The full chord length is 2 times the square root of the quantity r squared minus d squared. Meanwhile, one side of an equilateral triangle inscribed in a circle of radius r is r times the square root of 3. Written as an equation, it is this simple. Now require the chord length to exceed the triangle's side and rearrange. The result is remarkably simple. It is exactly equivalent to d being less than 1/2 of r. Thus, a midpoint inside the small circle means a long chord. Outside means a short one. We will use only this test from here on. Now let's implement random in the first way. Choose 2 points uniformly on the circumference. A chord is determined by its 2 endpoints on the circumference, so this sounds like the most literal method. Wherever the first point lands, rotating the circle gives the same picture. By rotational symmetry, we may fix the first point in one place. Let's place that fixed first point at a vertex of the equilateral triangle. For a chord from there to be longer than the triangle's side, the second point must land on the arc cut off by the opposite side. The 3 vertices divide the circumference into 3 equal arcs, and one of them is favorable. So when the 2 endpoints are chosen uniformly, the answer is 1/3. In other words, endpoint pairs that are far enough apart make up 1/3 of all pairs. No point received special treatment, and rotational symmetry was preserved. The calculation itself is flawless. But if we make a different coordinate for the chord uniform, the same question gets a different probability measure. The second method directly chooses the chord's orientation and its distance from the center. First, choose a random orientation. Draw the rotation angle uniformly so no direction appears more often than any other. Now consider a chord perpendicular to the radius in that direction. Their intersection is the chord's midpoint. Next, choose the distance d uniformly from 0 to r. We already found the long chord criterion. We just need d to be less than 1/2 of r. The full interval has length r, and the successful interval has length 1/2 of r. So the ratio is 1/2. So when distance along a radius is chosen uniformly, the answer is 1/2. Under this procedure, roughly 1 out of every 2 chords is longer than a side of the triangle. Making the distance d uniform is not the same as making the midpoint uniform over the area of the disk. The third method throws a dart at the disk and uses it to choose the chord's midpoint. Equal areas of the disk get equal probabilities. This time it is area, not distance or endpoints, that is uniform. Think of the dart's landing point as the chord's midpoint. Except at the center, each midpoint corresponds to one chord centered there. The chord is perpendicular to the radial direction. For a long chord, the dart must land inside the smaller disk whose radius is 1/2 of r. The area of a circle is proportional to the square of its radius. Having the radius makes the area 1/4 as large. When we compute the area ratio of the small disk to the large disk, pi and r squared cancel, leaving only 1/4. Therefore, when the midpoint is chosen uniformly over the disk's area, the answer is 1/4. It is the same circle and the same question, but now only about 1/4 and 4 is long. The third answer is also mathematically sound. Let's generate a large number of chords on a computer and check whether all three methods really converge to their own values. The original experiment sampled 200,000 chords with each method and counted the fraction that were long. From left to right, these results sample endpoints, distance, and area uniformly. The circle is the same, but the density of teal chords differs. Bright teal marks long chords and dark gray marks short ones. The middle plot is brightest and the right plot is darkest. In method 1, the observed fraction of long chords was 33.25%. In method 2, it was 49.98%. In method 3, it was 25.14%. On one line, the three theoretical values are 1/3, 1/2, and 1/4. Finite samples fluctuate a little, but each experiment landed right near its own theoretical value. Even when the original interactive experiment resamples 3,000 chords per method, each bar settles around a different target. So the answers did not split because someone made a counting error. We had called different probability experiments by the same sentence. To see the secret more clearly, erase the chords and leave only their midpoints on the map. The event of getting a long chord is the same as the midpoint falling inside the circle with half the radius. So the only reason the answers differ is that the three methods generate midpoints with different distributions. These three scatterplots erase the chords and leave only their midpoints. Teal points represent long chords. Method 1 places more midpoints outside the small circle. The endpoints must be far enough apart for the midpoint to approach the center. A pair of points chosen independently on the circumference is not very likely to land nearly opposite each other. Method 2 packs more points near the center because equal length intervals along a radius receive equal probabilities. When D is uniform, a narrow inner annulus and a wide outer annulus can receive equal shares of radial distance. Only method 3 spreads its points uniformly by the disk's area. That is why its success probability equals the small disk's area ratio. From left to right, the fractions inside the same small circle are 1/3, 1/2, and 1/4. Ultimately, uniform endpoints, uniform distance, and uniform area mean three different things. In mathematics, a rule that assigns a share of probability to each region among infinitely many possibilities is called a probability measure. The original problem never specified this measure. From the start, it lacked enough information to force a unique answer. Could symmetry identify the most natural measure? Jaynes took up that challenge. The standard conclusion is simple. Without a specified sampling measure, the question has no unique probability. But in 1973, physicist Jaynes went beyond simply saying there was no answer. The problem does not specify the circle's size. So Jaynes argued that a reasonable rule should give the same answer when the circle is scaled up or down. The problem does not specify the circle's position either. Jaynes required the same random law to apply when the circle is translated. No direction has a reason to be special, so the rule should also have rotational invariance. It should stay the same under changes of size, position, and orientation. In Jaynes's idealized random line setup, imposing all these additional invariance assumptions selects method 2's uniform distance distribution. That means the distance d from the center to the chord is uniform from 0 to r. Then the probability that d is less than 1/2 of r is 1/2, because the successful interval has length 1/2 of the total length r. In Jaynes's idealized experiment, sufficiently long straws are dropped randomly onto the plane, and only those crossing the circle are counted as chords. Under those added assumptions, this conditional random line model removes preferences tied to the circle's size and position, and leads to a long chord fraction of 1/2. But there is an essential caveat. Scale and translational invariance were not conditions stated in the original problem. Whether those symmetries are required, and whether other physical sampling procedures may be excluded, remains open to debate. Jaynes offered a useful principle for an ambiguous question, but the original wording did not produce one half by itself. So we still need to know how the chords are physically produced before deciding which of the three probability measures describes the experiment. Now let's step back and look at the larger target Bertrand aimed at with a single chord. The principle of indifference, popular at the time, says that equally plausible cases should receive equal probabilities. But with infinitely many chords, there are several ways to decide what deserves an equal share. The principle alone cannot determine the answer. A probability problem is not complete with only what it asks. It must also state how the sample is drawn. Even familiar phrases like tossing a coin or rolling a die conceal repeatable physical procedures. In modern data analysis, the rule used to sample the data in the first place is just as important as the formula. The same question can produce different numbers when the sampling method changes. Bertrand's three answers show that with just one circle. So the next time someone says to choose one at random, ask one more question. This question, posed in a Paris textbook in 1889, still matters whenever we work with continuous probability and statistics today. More important than the three numbers is the sentence that comes before them. A probability statement must tell us not just what was counted but also how it was sampled. If you enjoyed today's video, please subscribe, like, and turn on notifications. See you in the next story.